Again, question related to the diffraction of a light. So a blue light of a wavelength 4.5 exponent minus 5 meter incident normally at a diffraction grating which is having 100 lines per millimeter. Calculate the maximum number of order that can be observed. So what could be the maximum order? Like we need a value of n. So the concept is like what happened when the light is passing through this grating element, it diffract and then interference happen on the screen. So the maximum order when theta is equals to 90. That is the maximum order which we can observe. So this is a grating element or a diffraction grating, and we have the central maxima where n is equals to 0. Then from central maxima, the angle from a central maxima that we call theta to the fringes. So what could be the maximum value of the theta? The maximum value of a theta could be 90. That's a theoretical value, but the maximum value could be 90. So we just need that value. We have the lambda here. We have the lambda and we can find D. Always, even for Cambridge or Edexcel student, this is a common topic. And always they give you lines per millimeter or lines per centimeter and you have to work out D. So how to work out D? Because 1 millimeter means 0.001 meters and divided by 100. This will give us a value for D. So what is the value for D here when you divide? So 1 exponent 5 is the value for D. And the wavelength or a lambda is equals to 4.5 into 10 to the power minus 7 meters. And we are finding the order of the maxima, the maximum value. So just use d sine theta is equals to n lambda, where n is representing the maximum, like the order of the image. So d sine theta, my screen is lagging a bit, like actually my system is lagging a bit compared to the Zoom. So maybe you might not able to see first. So d sine theta is n lambda. So d is equals to 1 into 10 to the power 5. And sine, because for a maximum, we take that as a 90. Where n is the order of image, we don't know. And the wavelength is 4.5. Into 10 to the power minus 7. What is value for n here? So n is 22.2. So means, but n should be a whole number. So how many fringes, like maximum possible fringes we can see? That is 22. So that's a maximum possible of the fringes we can observe here. If you want to find the order for a minima, then it will be n plus half lambda. So we are finding for maxima, for a maximum number of orders, n is equals to, usually we determine for maximas, okay? If it was for how many minimas are there, then we'll use a formula n d sine theta will be equals to n plus half lambda. So maximum number for n, what we can have, like example, if this was a screen, and here was a grating element. So we'll have n is equals to 0 here, then n is equals to 1, then n is equals to 2, n is equals to 3, n is equals to 4, and maximum value of a n, the fringe, the maxima which you will observe, that will be n is equals to 22. So maxima, how many maximas we'll observe from the center? We'll observe 22 maximas. That is what we have to determine. Question 14. You are given with a diffraction grating with a 40 lines per millimeter. What will be D here? So it will be 0.001 divided by 40. What's the answer for D? What is the value for D? Because it is 40 line per, so 1 exponent minus 3 divided by 40. So it will be 2.5 exponent minus 5. Okay. So value of the D is 2.5 into 10 to the power minus 5 meters. And the question is now, the diffraction grating is mounted on instrument that can measure an angle within plus minus 0.1 degree. Like that can, smallest value it can measure is 0.1 degree. Can this instrument be used to determine the individual wavelength of a spectral lines of 589.6 nanometer and 589? So what we will do, we'll determine the order of the image, like we will determine the angle for, let's take like a first order for both of these wavelengths. And if that angle is more than 0.1, means this instrument can be used. If that angle, like first what we do, first what we did, like we will use the wavelength 589.5. So we will use a wavelength 589 and we'll observe, say first maxima is there, a zero order maxima, and then we'll observe another maxima where n is equals to 1. And we'll determine this angle, theta, for a first order. Then we use another wavelength. I'm drawing it here, but it will be done separately. Then we use another wavelength, like example 589 nanometer, and it will also have a central maxima. This is a grating element, and we'll have a central maxima, and we'll determine this angle theta for the new wavelength, which is 589 nanometer. And this theta, because whether it is able to determine the individual wavelength or the difference in the angle. So what we do, we determine the first angle, like the angle for the first order for both of them. And then we'll just simply take the difference of the angle. Like if the difference of the two angle is more than 0.1, it means it can be measured. Like we can separate like which is due to the wavelength 589 and which one is due to 589.5. But if the difference in the angle is less than 0.1, means this instrument cannot be used. So first we'll determine, like example, for a wavelength of 589, D is already known. So we use the formula D sine theta is equals to n lambda. And we are determining the angle for the first order, so theta 1. And D is there, which was 2.5 into 10 to the power minus 5. Sine theta 1, we are finding first order, and the wavelength which is used is 589.5. Because it's a nano, so it will be exponent minus 9. So sine theta 1 will be equals to 589.5 exponent minus 9 divided by 2.5 exponent minus 5. So what is the value for theta 1? Take a sine inverse. Tell the value for theta 1. What is this value? This is one way of doing the question. There's also another way of doing the same question can be done. Like what we can do, we can work out the maximum possible fringes which we will have. What is the value for theta 1 here? 1.3. Okay. 1.35 degrees. Okay. And we'll repeat the procedure for the second wavelength, which is also d sine theta 1 is equals to n lambda. But this time the wavelength is different. So 2.5 exponent minus 5 sine theta 1, n is 1, and this is 589 is there, exponent minus 9. So this will be sine theta 1 will be equals to 589 into 10 to the power minus 9 divided by 2.5 exponent minus 5. What is sine theta 1 for the new? Exactly 1.35. Yeah. So sine theta 1 is also 1.35. So means when we focus on the first order, look, when we focus on the first order, we cannot distinguish between these two. It's the same value. First value was a bit different. How much it was? This was, no, don't say the rounded off value. Okay, well, so means individual level, like when we are talking about the order, individual orders cannot be distinguished. Like you cannot distinguish which wavelength is from the like which spectral line is due to 589.6 and which one is due to 589. So means in terms of the first order or a second order, it cannot be distinguished. But then can a maximum we can distinguish? The maximum order can be distinguished. So first we'll find the value for n. Individual level, it cannot be. Okay, 1.35189. So means the first order, second order, third order, it cannot be distinguished because it looks like same. But can the maximum can be distinguished? So if can a maximum can be distinguished, like example, we use a formula d sine theta is equals to n lambda. Okay. And we find the maximum value for n. So how to work out the maximum value of n? If you want to work out the maximum value of n, the theta should be 90. Or the maximum order. And which wavelength I should use? Because I have two wavelengths, 589.6 and 589. Which wavelength diffract more? 589.6 or 589? Which will diffract more? Good, 589.6, because longer wavelength diffract more than shorter wavelength. So means the maxima, like if there was a 589, if it's a 589, it will diffract more as compared to 589.6 diffract more than 589. So if I need the maximum value of n, like the maximum spectral lines, so what should be the theta? Theta should always be 90. So again, we use a formula d sine theta is equals to n lambda. So d is the value, the spacing, 2.5 exponent minus 5 sine 90, because whenever we want to determine the maximum value of maximas, like highest value for maximas, theta is always 90. So n and the lambda, which lambda I should use? 589.6 exponent minus 9. Why I'm using this? Because this is the one which diffract more. So that is the maximum number it can have. Other will have, but this can have the maximum number. So when you solve for n, it is coming out 42.4. So 42.4 means I have to take as 42. So n is equals to 42 here. Means the order of image is 42. Now what I will do, for a n is equals to 42 and the wavelength of 589 nanometers, and for n is equals, for lambda is equals to 589 into 10 to the power minus 9 nanometer. 589 exponent 9 meter or 589 nanometer will determine the theta here and will determine the theta here. The d is the same. Because minimum, like what I said, the individual level, we cannot distinguish. Like I cannot distinguish n is equals to 1 for both of them as the angle is same. Now, can we distinguish from the maximas? Like the maximum pattern, can we distinguish that? So what is the theta for this one? Use a formula d sine theta is equals to n lambda. What is the value for theta? Substituting 589.6 589.6 exponent minus 9. So this is giving you 82, okay. 82.1 degrees. When I find the theta for 589 exponent minus 9, what is this answer? This is 81.7. So means the maximas, when the 42 maximum is there, like if maximum number of, it's 42, the maximas will be different at different positions. One will be at 82. One will be around 82. Another one will be around 81.7. So this is 81.7. Okay. And this is 82. Okay. So when you substitute the values, this is coming out 82.1 and the other one is 81.7. When you take 589.6 exponent minus 6, you got 82. The maximum will be at 82. Exact, and this will be maximum will be about 81.7 degrees. So hence the maximum, when we take a difference of these two values, 82.7, so this is about 0.4 difference. So from their maximas, we can distinguish which is from 589.6 and which one is from 589. But from individual separation, it is not possible. It is only possible when we focus on their maximas. Their maximas will be different. So we can identify which one is from wavelength 589 and which one is from 589.6. But individually, like for a first order image or a second order image, it cannot be distinguished by this instrument. Is it clear? Discussion? So what we did, the question was, can this instrument, if the central maxima is the same way, why the angle differ by more value? Why the angle differ if the central maxima is more in the same position, why the angle differ? Because the diffraction depends on the wavelength. The longer wavelength diffract more, spread more. So the angle increases between the maximas. The first and the maxima, this angle will be higher. But if the wavelength is shorter, then the angle to the maxima will be minimum. Smaller value. That's why even though the order of image is same, but their wavelengths are different, so we can distinguish by using the instrument. So the question was, can this instrument be used to distinguish between the two wavelengths of 589 and 589.6. So what we did, individual level, like for the first order or second order, it cannot be. But for the maximum order of image, yes, this instrument can be used to distinguish between the two wavelengths. Is it clear? Anyone having a question or doubt in this part? Yeah, it did not tell us to compare the maximas, but we have to compare both of them. We have to compare because maxima is a criteria that's the maximum number which we can have. When the two waves spread passing through the slit, it will spread. So the maxima is a weight we can compare the two waves, their diffractions, and then we can estimate according to the instrument. Because individual n is equals to 1, it cannot be compared. But n is equals to maxima, yes, it can be compared as there is a difference in the maxima angles. So in short, if we are using a diffraction grating and we use the wavelength which is 589.6 nanometer, the angle from the central maxima was like the central maxima to the maximum order image, that was 82.1 degrees. Then we use, and the same instrument is used, and we use a different wavelength which is 589 nanometer, which also diffract, but that is diffracted about 81.7 degrees. So the question was, this instrument can measure up to 0.1 degree accurately. So can this instrument, because after that we will not have a image like a fringe. So that is a maximum fringe order of the image, and this is a maximum order of image. So can this instrument be used to distinguish which pattern is from 589.6 and which one is from 589? Yes, this instrument can be, because the difference in the maximas is 0.4, which is more than the least count of this instrument. So it can record this difference. But individual level, when we were talking about like a first order, say n is equals to 1 here and n is equals to 1. So n is equals to 1, it cannot distinguish because 1.35 degrees was this, and this was also 1.35 degrees. N is equals to 90, it's a theoretical, because here if you remember, when we work out n is equals to 90, the order of the image was 42.4. So 42.4 will be here, but this will be 42. The order, but there is no order of image 42.4. It's always a whole number. So we took a smallest value. So that's a maximum, like the order of image which we will get. Any doubt in this part A? Then we have part B. A white light is incident at a grating element. Estimate the angle between the extreme ends of a spectrum for a 10th order maxima. Actually, a white light is used. So if a white light is a combination of 7 colors, violet, indigo, blue, green, yellow, orange, and red. So we want the that for a 10th order, we want a diff angle. So we have the wavelength, which is having the maximum wavelength. You have to learn the order: violet, indigo, blue, green, yellow, orange, and red. What is the wavelength of a red? 700 nanometer. Memorize this value. What is the order of the violet? It is 400 nanometer. And for a 10th order maxima, we need the angle between the extreme ends of the spectrum. Spectrum means band of color. Like, look, so this is the diffraction grating, and here is a screen. So red is having the longest wavelength, so it will diffract more. So this will be So we'll have a Vibgyor, violet, indigo, blue, green, yellow, orange, and red. So red will diffract more because it is having a longer wavelength, and violet will diffract less. So what we want for a 10th order image, we want this angle between the ends. Okay. So first we'll find the angle for the violet, then we'll find the angle for the red, and we just take a difference of the two angles to know the theta. Is it clear? So this wavelength is lambda, this wavelength is lambda, n is equals to 10. No, we will not add the angle because we need the angle between the extreme ends of the spectrum. What are the extreme ends of the spectrum? One end of a spectrum will be violet and the other end will be red. So when a white light, which is a combination of 7 colored spread, so violet bends. So we have violet, indigo, blue, green, yellow, orange, and red. So we want this angle. So we'll take a central maxima, like theta is an angle from the central maxima. So we'll find the angle of the violet and then we'll find the angle of the red for the 10th order. And we just take a difference of the two angles to know this angle between the two extremes of the spectrum. And same formula we use, d sine theta is equals to n lambda. It's a continuation of the question. No, violet will not go below the central maxima. Violet, it's not going below the central maxima. When these light passes, this is a 10th order. Like what actually happened, it's on the screen you will have 7 colors. So first we'll have a region where we'll have all these 7 colors like violet, indigo, blue, green, yellow, orange, red. That is one maxima. That is a central maxima. Then we'll have a minima, again central maxima, which include red to violet. That is a first order image. Then again, violet to red, that will be the second order image. So what we have to do, we have to find the angle between the 10th order, like as we go on. So central maxima, then, so let's say this is n is equals to 10. So in n is equals to 10, we'll have violet and red. We'll determine the distance angle from the maxima for the violet. Then we'll determine the angle of the red, the 10th order red from the maxima, the central maxima, and take the difference. Is it clear? Yeah, for red, for violet, the theta is 9.2. That's right. So one of the student already solved. For a red, the theta is 16.3. That's correct. And for violet, the theta is 9.2. That's also correct. And you take a difference. So it's about 7-degree difference in the 10th order maximus which is having the color violet and red. So means when the 10th order maxima is there, because in this case on the screen, we'll have a maxima, the first order, like 0 order maxima, which will have the color violet to red, all. Then we'll have another maxima, like minima, then maxima, which will also have color violet to red. Then we'll have another maxima, which will have all the color violet to red. Then we'll have another maxima, which will have color violet to red. So let's say that this is a 10th order. So from a central maxima, we find the angle of the 10th order violet, then the angle of the red, 10th order red, and we just take a difference of these two angles to know what is the angle between the 10th order violet and red. That is what the question states.